Hello Year 13, hopefully the computer's finished updating itself now and we're ready to go. Simple harmonic motion. This one is about acceleration. So, we had the bob, which was on a pendulum, and it was going up and down, up and down. At the equilibrium position, the forces on it were balanced. Why? Because at that point, the up force and the down force on this are equal and opposite, so it's balanced. That means it doesn't accelerate. Newton's second law said that acceleration is to do with the amount of force you put on it. If you've cancelled your forces out, you haven't got any force, you've got no acceleration. When it's up at the apex, however, if it was something like a spring, you've pulled the spring as far as you can, or as far as you're going to. That means that the force is going to be at the biggest. So, remember the rules of simple harmonic motion. The larger the displacement from the equilibrium position, the larger the force on it, which means that up here at the apex, you will have the biggest force on it, pulling it downwards. If you don't know what I'm talking about, you need to go back to the first video and have a look at it. The one with the spring and then this thing bouncing backwards and forwards. All right, so what did we do? We had a reference circle going anti-clockwise with a bob on it, and we had our pendulum swinging backwards and forwards, and we had the sunlight coming this way shining onto the wall, and we could see the shadow, and you could see they matched each other, which was great. So what that means is the position of this must relate to the motion of this. So when we're looking at this, we can now use the reference circle to do the maths calculations, which makes life a bit easier for us. You might not think so, but it really does. So when we're looking at this, let's just get some ground rules in. So at the equilibrium position, acceleration is 0. Why? Because the net force on it is 0, which means there'll be no acceleration. Great. Up here, because you pulled the string as far as you can, or as far as you're going to, it means it will have maximum acceleration downwards. The force is a maximum downwards. Notice I put it downwards because that's the direction it is, which means if we're looking at a reference plane, then there will be a minus, won't it? We'll come back to that later. All right, on our reference circle, this is a circle, so we can go back to some of the circular motion we looked at in year 12. Centripetal acceleration is towards the centre, which would be this way. This angle here is displacement, and that arrow there represents the acceleration of simple harmonic motion. That's why I've written SHM next to it, which stands for simple harmonic motion. All right, if you take that little bit there and make it into a triangle here, it starts to make a little bit more sense. This here is the centripetal acceleration that way. That is the displacement angle here in radians, because we're working radians now. And this is acceleration of the simple harmonic motion. So that's the acceleration of this object here. All right. The formula for it, actually, before we get to the formula, let's look at this. So, centripetal acceleration, which we learned about last year, you were told it was v squared over r. It still is. But that is for linear motion. So if you're driving around a corner in a car, then you're going to require a force to push you around the corner. This is normally provided by friction on the tyres. If you're on a banked corner, as you know, it will be provided by some of the normal force, the horizontal component of it. Now, the reason we did rotational motion first is because you will know what this means. Linear to rotational means that you multiply by the radius. So for linear stuff, to get the linear velocity, we would multiply the rotational velocity by the radius. The radius, in this case, will be the amplitude in meters. So that's the amplitude of simple harmonic motion, which will be how much it moves up and down here, which will be the same as the displacement reference circle's radius. All right. So A is the amplitude in meters. So when we then substitute this in, we change the R to an A, and we are going to square that. We're going to square R and W. So we get, because R is now A, you get A squared, W squared over R. And then with some amazing algebra, we can get rid of the R. Why? Because A is the same as R, because we said so here. So the A squared, and the squared bit disappears, and it goes to just AC equals AW squared. And then it's a minus. And remember I said we're coming back to the minus. It's a minus because acceleration is downwards here. Now the reason that is because we are measuring all this from the equilibrium position. So we're starting here and we are going this way round, which means that when we start, this will be a minus. It's downwards. Up is positive, down is negative. It normally is. Okay, so that then becomes AC equals AW squared, and it's a minus because it's downwards. And now you can look at this formula here. So this triangle here, which came from here, AC is there, it's the hypotenuse, and a simple harmonic motion is the opposite. So we can use sine. Here you go, sine equals the opposite over hypotenuse, which means sine theta equals a simple harmonic motion divided by AC. But AC equals AW squared. Let's put that one in. So sine theta equals a simple harmonic motion divided by AW squared. Exciting stuff, isn't it? Oh yes. Here we go. Rearrange it. You get AW squared equals sine theta. AW squared sine theta equals the acceleration of the simple harmonic motion object. And if you want to, you can write it the other way around and it will still be correct. This formula here, that's what you get on your exam paper. Oh God, there's some more stuff over here, goodness. This is just a reminder of some of the stuff we talked about. So at the apex, acceleration centripetal will be the same as the acceleration simple harmonic motion. Why is that? That is because you will be up here, so centripetal acceleration will be downwards, and guess what? The simple harmonic motion object, our little bob, would have been up here and would have had its maximum force on it downwards. And they're in the same direction and they're the same size. Okay, so that's what that says. At all other points though, the simple harmonic motion acceleration will be less than AC. That's because it's in a different direction. At the apex, simple harmonic motion equals the amplitude times rotational velocity of the reference circle squared. And at the equilibrium position, the simple harmonic motion's acceleration will be 0. Why? Because it's at the equilibrium position, which means the forces are balanced. There is no net force on it. Newton's second law said if there's no net force on it, it won't accelerate. That's why acceleration is 0 at that point. Okay, well, that was quite a bit. See you next time for the graphing of it all.